Hi, we are building the agentic grid orchestration for electric utilities. The job of an electric utility has never been harder. You have millions of customers that you need to serve every day. You have billions of dollars of assets from transmission lines to rooftop solar. You have constraints like regulatory constraints, market constraints, and actual physical constraints of the grid. You have your objective function of maximizing profit, but at the same time, you have anomalous events. For example, there could be a cloud cover, which means your solar production drops, or there could be an asset failure. So electric utilities every minute are ingesting millions of data points and taking a decision. And we wanted to build an agentic grid orchestration system that does it for electric utilities. So this is the landing page. When you click on it, you see what an operator at an electric utility would see, which is peak demand, current demand, what is the system stress, and the grid topology. And they would talk about the data sources. At the same time, you can see which line loadings of a grid are extremely stressed. On the back end, we have 5 agents, each with their own optimization function, and then a master agent that is taking a decision on what should the electric utility do.
So we wanted to emulate an actual operating electric grid, and we took an IEEE 123 bus system that represents some part of California. This contains real power plants that generate load, that generate power. We have load centers like residential and commercial hubs. We model outages, so this is a live electrical system. When we go into the platform, we can start actually simulating the system. There's some losses that incur because of technical and transmission distribution losses. The core part of this is the 5 agents. Just like any actual utility operator, so these are large teams with hundreds of people. There's a strategic planner that's making sure demand is always met by supply. There's a tactical dispatcher, which means that's done at the lowest cost. There's an asset intelligence platform, so what if a tree falls in a wire and it's wiped out? So all of these agents work in coordination, not in a silo, and they each have their own objective function and tools that they can call. They simulate what the impact of their action is on the grid, and they model the scenario about 10 to 12 time steps ahead to see, okay, if I take this action, what would happen to the resulting power system? So because we did not apply extensive fine-tuning, we see that these agents aren't actually doing a really good job for some of the variables. Voltage stability is down, power losses are down, they're not really balancing load, and so this is one of the biggest problems we face is without fine-tuning, when we apply GPT-5, as the agentic layer, it does not really optimize functions in every single time step. It usually takes the safest path away. What we'll see over here is that at any point of time, every single agent is optimizing for their objective function. So the strategic planner will try to switch a capacitor bank. The tactical dispatcher will activate a BESE, a battery discharge. What we want to optimize for is how do you layer objective functions one after the other. So what you want to do is meet reliability, do it at the lowest cost, and ensure continuous uptime.
All right, thank you, Team Pravah. Unfortunately, we are at time.
We are backed by parent conviction and looking for founding MLEs and engineers. If this is a problem space that interests you, please go to their website and reach out to us. Thank you.
Judges, do we